Well, hello. Whoa. That is exciting. Unused printers. Okay. Well, hello, good people. Today we are talking length contraction. Did I spell that right? I totally did. Length contraction and mass dilation. In our last video, you learned that time is relative, that the way that I perceive your time and the way that you perceive your own time is different if we're in different moving reference frames. If your frame of reference is moving differently than my frame of reference, well, then I will see your time differently and you will see my time differently. I'll see your time slow down, you'll see my time slow down. But to me, my time is still going normal. To you, your time is still going normal. But today, we're going to talk about how that applies to length. If you were to take this meter stick here, wait, let me make this big. If you were to take this meter stick here and you were to measure the length of this meter stick, you would see that the length of the meter stick is a meter. But if you were to measure the length of this meter stick right now, then you would see, sorry, I was like, did I damage my drywall? We're all good. If you were to measure the length of the meter stick while it's moving, then you would see that the meter stick is a little bit shorter than normal. This is because of length contraction. It turns out that time gets dilated when you're in differently moving reference frames, but also length changes when you're in differently moving reference frames. Let's look at some equations here. In our last video, you learned that if it comes to time dilation, we know, I'm going to go light green here. We know our equation for time dilation looks something like this. Hang on, team, let's get that out of the way. You really think that they could make a better system for color changing here. We know that time dilation, delta T, the amount of time that passes for you looking at someone else when you're looking at their clock, you would see it's their time that they see when they look at their own clock divided by the square root of 1 minus v squared over c squared, where v squared is the speed of them and c squared, or c is the speed of light. Well, we won't derive this equation today, but something that you need to, I will show you this equation. If you'd like to see the derivation, please let me know and I'd be more than happy to show it to you. But we also get length contraction, which says that the length that you see the meter stick at is equal to the length that the meter stick sees the meter stick at times the square root of 1 minus v squared over c squared. Looking at this equation, do you see that this equation might very simply be derived from the same sort of situation that we used last time where we had like some nice right triangles and did a little Pythagorean theorem action? Same sort of derivation to find this equation as we did to find our time equation. The length of the meter stick in your perspective is equal to the length of the meter stick in its own perspective times the square root of 1 minus the speed of the meter stick in your perspective all over c squared. Here's what this means. If you look at a moving meter stick, you will see the length of that meter stick as being shorter. But if I'm running with a meter stick and I'm looking at my own meter stick, I would see the length of that meter stick as being the normal length of a meter stick, 1 meter. So watching from the outside, you'd see that a meter stick when it's moving looks like less than a meter. Watching from the inside, from the same reference frame as the meter stick, I would see that the meter stick moving has the same length as it always does. That follows our first postulate of special relativity, which says that the length, that in its own reference frame, in an inertial reference frame, as long as your reference frame is uniformly moving at a constant velocity, the laws of nature are always the same as they are in a non-moving reference frame. So for example, if you're looking at a meter stick and you're moving at a constant velocity, the laws of nature are still the same. That meter stick should still be a meter. But if you're looking from an outside perspective at that moving meter stick, you would see it as less than a meter. A fact that you need to know about length contraction, yes, do write this down, is that length contraction occurs in the direction of the motion. Length contraction occurs in the direction of the motion. Let me show you what I mean by this. Okay, here we go. If I have this meter stick, wait, let's make it nice and big here. If I have this meter stick and say that I move it to the side this way, when I'm moving it to the side this way, this meter stick will contract in length this way. It will get shorter. What will not happen to this meter stick is that as I move it this way, it will not get skinnier. It will only contract in the direction of the motion. As far as the meter stick knows, top to bottom, it's not moving at all. And you looking at that meter stick would say top to bottom, it's not moving at all. It only contracts in the direction of the motion. So if it's moving this way, then you have that the length will contract this way. The meter stick will get shorter. Hey, here's a question for you. Suppose that I took this meter stick and I threw it up this way. Is that meter stick going to get shorter, longer, skinnier, or fatter? You should say skinnier, Miss Wilson, because its length is going to shrink in the direction of its motion. So as you move it up, it'll shrink this way just a little bit, and so it'll be just a little bit smaller, it'll be just a little bit skinnier as it goes up like this. Try this one. Suppose that I take this meter stick and I throw it up like this. If I throw the meter stick up like this, well, then it's going to shrink in the direction of the motion. This meter stick is going to be shorter this way. Try this one. If I have the meter stick up like this and I throw it to the side like this, when I move it to the side, it's going to get skinnier this way. Notice that your length is always getting shorter or skinnier in the direction of the motion. It's never getting longer, which corresponds to our equation right here. If you take a look at our equation, if you have a v here, this is always going to be 1 minus something, which means you're going to get something less than 1. Square root of something less than 1 is still less than 1. So you get L naught, which is the length of the meter stick in its own perspective, times something less than 1 gives you a length that is less than the length of the meter stick in its own perspective. So anything that moves will shrink. If you're watching a moving thing, then its length will shrink. Now, in normal everyday life, we say that we don't see this very often. It's not as though you see a car going down the road and you say, wow, that car looks so much shorter going down the road now than it normally does. No, it looks about the same to you, and that's because when we were going non-relativistic speeds, in other words, if v is not very big compared to c, then something small over something big turns out to be something very, very small, like very close to 0. 1 minus basically 0 is basically 1. Square root of basically 1 is basically 1. L naught times basically 1 is basically L naught, and so L equals basically L naught for non-relativistic speeds, for small speeds. But when your speed gets up really, really high, then you actually do really start to see things shrink. If this meter stick is going at 87% the speed of light, this meter stick will be half a meter long. If the meter stick is going at 99.5% the speed of light, then this meter stick will be 10 centimeters long. Now let's be very clear. When I say that this meter stick, when it's going 99.5% the speed of light, is going to be 10 centimeters long, do I mean to say that the meter stick is actually 10 centimeters long? Yes, that's exactly what I mean to say. The meter stick is actually 10 centimeters long. Remember when I was throwing a baseball out my car sunroof? If I'm throwing a baseball out my car sunroof, is the car going 40 miles an hour or is the baseball going 40 miles an hour or is it going 80 miles an hour? Yes, both are true. The person who catches the baseball in their mitt would not say, oh, it just feels, I only perceive it to be going 80 miles an hour, but it's actually really deep down, we know it's going 40. No, the person who catches it in their mitt would say it's actually going 80 miles an hour. And when I threw it with my arm, I would say, I actually threw it at 40 miles an hour. I don't have a good arm. I have a great arm if I can throw it 40 miles an hour. But I would say I don't have a good enough arm to throw it 80 miles an hour. I have a good enough arm to throw it 40 miles an hour. So I would say it's actually going 40. The person who catches it says it's actually going 80, which is actually the physical reality. Yes, both. Both are actually the physical reality. Now here's a little thought experiment that is a classic thought experiment from relativity. This is a classic one, and if you ever study relativity, then you will likely hear this thought experiment again because it's just a fun one. Suppose that I had a barn, and that barn was when it's sitting still. Suppose that I have a barn. We'll make it a red barn because barns should be red. Suppose that I had a barn. Here it is, and my barn is this big. Ta-da! Now suppose that I also had here's the roof of my barn. Yay. Now suppose that I also have a ladder. And suppose that my ladder is equally as long as my barn. So suppose that I have a ladder that is exactly well, I said exactly, and then I didn't draw it exactly. Let's try again. Exactly as long as my barn. Like this. Here's a question. If I were to take this ladder and I were to put this ladder on my head like this, and then, actually I'm going to go this way. Suppose that I were to then, with the ladder on my head, I were to run through the barn, holding the ladder above my head at a very, very fast speed. Let's say that I could run very, very quickly. Let's say that I could run with a constant velocity that was near the speed of light. That would be very impressive of me. Maybe something like 50% of the speed of light or 70% of the speed of light. You would say, wow, Miss Wilson, you have great legs. What a runner, what a track star you are. And I would say, wow, oh my gosh, thank you so much. But check it out. If I'm running very, very fast through the barn at a very, very fast speed with the ladder on my head, here's a question for you. Would the ladder fit in the barn? Well, you should say, depends on where you're standing, Miss Wilson. You should say, if you are watching the barn and you're watching the ladder move through the barn, if you are in the reference frame of the barn, which is standing still, and you also are standing still watching the ladder move through the barn, you would see the ladder contract in length because you would say it's moving. And so you would say, yes, the ladder definitively fits in the barn. But from my perspective, if I'm running with the ladder on my head, I would say, actually, this ladder looks to be the same length that it always is. It is always this exact same length, and so the ladder seems to be the same length that it always is, and I do not see any length contraction. But remember, to me, if I'm going at a constant velocity, I feel as though I'm not moving. But if I look at the barn, I would say I'm not the one that's moving. Barn, you're the one that's moving. It's as if I'm standing perfectly still and the whole barn is going backwards. So I would say I am still and my ladder is the same size. It's the barn that's moving backwards. And I would say the barn is moving backwards, and so I see the length of the barn contract. So I would say not only does my ladder not fit, the barn got smaller. So the ends of my ladder are sticking out of the sides of the barn. Here's the question. Does the ladder fit in the barn or not fit in the barn? Yes. It does both fit in the barn and not fit in the barn. Both are true. Both are really, actually, physically true. Because I see the barn contract and you see the ladder contract. Now, do you see why to light it takes no time to get anywhere? Imagine this. Imagine that light is going at the speed of light, because it is. If light's going at the speed of light, imagine what light would see as light makes its way through the barn. Here's a little photon that is a great, wow, okay, whoa, okay, let's all just relax. Maybe that's one of the most accurate pictures of a photon I've ever drawn, honestly. Okay, wait for it. Okay, here's a little photon. As that little photon moves through the barn at the speed of light, that little photon would see the barn contract, but watch how much. The photon would say, I'm not the one who's moving, it's the barn who's moving, and the barn's moving backwards at the speed of light. So the little photon would say the length of the barn, in the photon's perspective, is equal to the normal length of the barn times the square root of 1 minus c squared over c squared. Well, c squared over c squared gives you 1, and 1 minus 1 is 0, and the square root of 0 is 0. So the light would say that the length of the barn is 0. The length of the barn is 0. So the light says, yeah, of course it takes me no time to get from here to there. There is no such thing as here and there. There's only here, and here is everywhere. And so, of course, light can be omnipresent, because to light, distance is trivial. There's no real such thing as distance. To light, here and there are the same. The length between them is none. And so this is why light says that it takes no time to get anywhere, is because it says there is no such thing as everywhere. There's only here. Now, let's go ahead and try a practice problem. Actually, I'm going to erase my... Actually, no, I'm just going to pull up a new page. Let me grab a new page really quick, and I'll pause and come back. One sec, team. Okay, here's a practice problem for you. Let's say that I had a meter stick that has a length of 1.00 meters. And I want to know, how fast do I have to throw this meter stick so that the length of that meter stick in my reference frame is 0.38 meters. Well, before we start this problem, please start by identifying which one is L and which one is L naught. Hey, you said that 1 meter is L naught because that's going to be the length of the meter stick in its own reference frame. L is 0.38 meters because that is my perspective on the meter stick's length. And V is how fast the meter stick is going. Okay, let's take a look. We start with our original equation, which says that L is equal to L naught times the square root of 1 minus V squared over C squared. I am trying to get V squared by itself, so I'm going to need to do a good amount of rearranging here. Let's start by dividing both sides by L naught. I get L over L naught is equal to the square root of 1 minus V squared over C squared. My next move, if I'm trying to get that V squared by itself, I'm going to get rid of that square root, so I'm going to square both sides. When I square both sides, then my square root goes away. Now I want to get that V squared over C squared by itself. So what I'm going to do next is I'm going to move this over to the other side and move the V squared over C squared over to the other side as well. So I get V squared over C squared is equal to 1 minus L squared over L naught squared. Then, to get V squared all by itself, I'm going to multiply both sides by C squared. I get that V squared is equal to C squared times 1 minus L squared over L naught squared. And then I am going to take the square root of both sides in order to get V by itself. Take the square root here, take the square root here, and I'm going to get that V is equal to, hey, a C squared square rooted. I could pull that out in front and just call it C. Times 1 minus L squared all over L naught squared. Now, you can take the time to plug in numbers here. When you plug in numbers, you plug in for C 2,997,92458 meters per second, and I am totally so very much going to run out of room here, times 1 minus my L squared is 0.38 meters squared. My L is 1.00 meters. I just forgot to put my parentheses around here. Squared. And you can see I'm so super out of room, but you could imagine that that's squared on the bottom. It doesn't really matter though because it's a 1. Plug it into your calculator and you should get 2.8 with good sig figs times 10 to the 8th meters per second. Hey, check it out. You know that the speed of light is basically 3.00 times 10 to the 8th meters per second. This 2.8 times 10 to the 8th meters per second, wow, we are for sure nearing the speed of light here in order to get this thing to be 0.38 meters. And that's a little bit of a practice problem for you. Now we have one last topic here before we close it out today. And our last topic is on mass dilation. Here's the thing about mass dilation. Try this experiment. Suppose that I had this 1 kilogram mass sitting right here. This 1 kilogram mass sitting right here currently has a mass of 1 kilogram. But if I were to take this 1 kilogram mass and, not drop it, but I were to toss it going relatively quick, this 1 kilogram mass would then have a mass that is more than a kilogram. You found that time is relative, that length is relative, and it turns out that mass is also relative. And we got an equation for it that looks similar to our others. Here's the equation for it. The equation for mass dilation looks like this. We say that the mass of something is equal to the mass that it is in its own reference frame all over the square root of 1 minus V squared over C squared. You say, wow, that looks awfully familiar to your time dilation equation. It's so very true. They are all super deeply related. Now, a lot of students look at this and they say, okay, Miss Wilson, I know that V equals delta X over delta T. And they say, it makes sense to me that you would get some time dilation and that would be related to your V. It also makes sense to me that you'd get some length dilation because of your velocity, but there's mass nowhere in this equation, so it doesn't make sense to me that you would have mass dilation. Well, the reason why you have mass dilation is really deep down. Mass dilation is not mass dilation. I took a class in college that was called Spacetime and Quanta, and we never talked about mass dilation. Instead, what we talked about was momentum dilation. we know that momentum is equal to mv. And if you have momentum dilation, then you have m naught v all over 1 minus the v squared over c squared, square root that whole denominator there. Your v's cancel out here, and so then you get this mass dilation equation. Here's the reason why you get mass dilation. If you look at this equation, kinetic energy is equal to 1/2 mv squared. You can see why mass dilates, and here's why that's true. You can keep dumping kinetic energy into an object if you keep trying to speed up that object. You can keep dumping as much kinetic energy as you can apply a force over distance. There is no limit to how much kinetic energy an object has, but there is a limit to its speed. The speed limit of the universe turns out to be c, and we'll explain why you can't go faster than c momentarily. Well, there are actually a few different reasons for explaining it, but you can't go faster than the speed c. So as you dump more and more energy in, eventually that energy isn't going to go towards increasing the speed anymore, because speed has a speed limit. But what it will go to is it will go to increasing the mass. So as you dump more and more and more energy in, you'll start increasing the mass of the object. That energy will turn into mass in accordance with E equals mc squared. Now, let's look at why it is actually very impossible to travel the speed of light or faster. One reason you can tell just by looking at this equation, well, hey, if I put in a 1 minus, I put in a c squared here or greater than a c, put in a number greater than c, and don't you get an imaginary number here, and you say, that's not possible physically. So it's not physically possible to go faster than the speed of light, because then according to this equation, well, you'd get a number that's imaginary, and that is like super not cool. But also check this out. As I go faster and faster and faster, as I get an object going faster and faster and faster, that object is gaining mass, which means it's also gaining inertia. The more mass it has, the more inertia it has. You'll remember Newton's second law, that F net is equal to ma. If I increase the mass of an object, if I want to keep accelerating that object, I have to keep applying more force because the inertia keeps growing. So, to accelerate an object with very little mass takes very little force. But then, if I want that object to go a little bit faster, and giving it more speed makes its mass more. Well, if I want it to go a little bit faster, well, I just made the mass more, so it's going to take more force. Then when I push it a little bit harder, add a little bit more force, the mass goes up a little bit. Now I have to push even harder. Adds more force. The mass goes up. Or adds more mass, the mass goes up. Adds more inertia. I have to push it even harder. Goes faster, mass goes up. So now I have to push it even harder. Goes faster, mass goes up. So here's what happens. The harder and harder and harder you push it, the more and more and more mass it gains. So the harder and harder and harder it is to push it the next little bit. If you look at this equation, as the speed of something approaches c, the denominator approaches 0, which means the mass of that thing is approaching infinity. The amount of force that it would take to push it that last little bit, to get to that last little bit of speed so that it gets up to c, the amount of force that it would take would be infinity force, because it would have infinity mass. So you could see why it's never going to be possible to push something with mass up to the speed of light. Because once you get close to the speed of light, it takes infinity force to push it all the way there. That is why the only thing that could travel at the speed of light is something that has no mass. Something like a photon. Well, that's all for today, folks. We talked about mass dilation. We talked about length contraction. The main story is when something goes fast relative to you, that thing is going to shrink. When something goes fast relative to you, its mass is going to grow. And that's pretty much the gist of it. Weird stuff doesn't really make a lot of sense, but that doesn't keep it from being true. That's all for today, folks. I hope you have a wonderful, wonderful rest of your day. Bye, good people.